All right, so welcome to Lecture 3. We'll talk about CPU policy, and in particular, we're going to talk about scheduling. So maybe as soon as possible, read the sections on direct execution and CPU scheduling. So two very different ways of scheduling the CPU for execution. Let's do a review first. We'll take a look at some of the things we've seen before. Basically, what is an operating system? It is software that helps other programs control computer hardware, interact with users, things like that. What are these other programs? They're almost always applications. Of course, there are other things like device drivers, things like that. But let's just say it's the kernel mainly of the operating system and then applications. Those are the two main things. What exactly is an application? It's just any program that allows a computer user to do things that the computer user wants. And the way things are set up, if you have an operating system and an application, applications cannot act without permission from the operating system. So everything, like every single file access, things like that, has to go through the operating system so that the operating system can control access to all the resources. Also, we talked about CPU virtualization before. Remember, the goal of virtualization is to be able to run many processes on some small number of CPUs or cores. So typically, you have a large number of processes, very small, not very small, but a small number of CPUs, like 2, 4, 6, 8, or maybe even more. So the abstraction we used was that of a process. Each process sort of gives the programmer the illusion that you have access to the entire machine, but you really don't, because you have many things, many processes running at the same time. How does the operating system support this abstraction of a process? There's a lot of support in the kernel and in the CPU to support this. So one of the things we saw earlier was that every process has a process state. Remember, a process is just a program that is currently running, and each process has a state which includes all of the memory, which has instructions and data, and all of this is called address space. In addition, it has registers in the CPU, for example, things like the program counter, stack pointer, and typically there's a ton more registers. These are the two sort of important ones that we have to keep track of. And then also each process has a list of files that it has open at any given time, and then other resources that we'll see more of later. Okay, so there's direct execution where the operating system says, okay, user process, run directly on the hardware. And this is probably, you've all seen the DOS operating system, maybe if not in the actual DOS, maybe DOS box or something like that. So there's a lot of problems with using this DOS model of allowing a process to do anything at once on the hardware. If a process can do anything, then it can break security. It can change files that belong to other users, or maybe the super user, if there is one on a system that allows direct execution. It can change settings. It can set up a loop that just sits and uses the CPU forever. So that's not fair to other users if there are the users. So you can sit in an infinite loop if you had a DOS model of execution. Also, efficiency might go down because this is one thing we'll talk about later. I/O, or input output, especially when you're dealing with files or slow disks, that's going to be slow. And so if you have a CPU that's just waiting for I/O to happen, that's not efficient. The solution to all of these problems, that is problems of direct execution, is to have the operating system have a lot more control over what gets used and what processes can do. So, and that's really the more interesting solution that we're going to look at. Also, we looked at how to control process execution. At system boot time, the operating system sets up what are called trap handlers. And when each process runs, the operating system is involved in every system call because there is an elevation of privilege. So the operating system is also involved on timer interrupts to switch processes, like on Linux most of the time. Each process gets about 200 milliseconds, and then after that it has to give up its time slot and allow some other process to run for 200 milliseconds or less if you're doing I/O. And the idea is that processes time share a single CPU. So you may want to review some of this if you don't remember, or if it doesn't look familiar. Especially you want to try to review what a context switch is. When is it used and why is it used? Definitely that's something that's very important, that is going to come up over and over. So if you don't recall, definitely stop now and take a look at what context switch means. It's pretty straightforward. Okay, and we talked about how the operating system maintains the state of execution of every program. Every process is in one state at any given time. It's either when it's running on the CPU, taking up CPU cycles, it's in a running state. And then if, let's say it's 200 milliseconds, then it's descheduled, and some other process will start to run. When it's descheduled, it sort of goes into a ready state, which is ready but not running. And then when this process gets its time slot after some other processes run and it's in the ready state, then the scheduler can come in and say, okay, this one hasn't had a chance to run, so I'm going to give it a chance to run. I'll schedule it and it starts running. If you are running and you have to open up a file and it's on a slow system like the hard drive or something, then the operating system recognizes that, well, this is going to take a long time. And whenever it has to do disk I/O, the problem is that hard drives, we'll talk about this more later, but the access time, that is the time that it needs to find the data that it wants to read or write to, depends a lot on the disk rotational latency. So if you have a 10,000 RPM disk, which is pretty fast, that revolutions per minute, you can convert that to a time. That's about 6 milliseconds. So 6 milliseconds to rotate. That is a long time when you're talking about 3 gigahertz processors. So processors these days run at 3 gigahertz, or let's say 4 gigahertz. That's a quarter of a nanosecond. And 6 milliseconds, that means you could be running a lot of instructions while waiting for this disk to rotate to the right spot. So that's why processors or operating systems these days, when you see a process trying to read something from a file, it'll say, okay, that's it. You want to be blocked. I'm going to let the I/O and the disk and things boot up. And so what happens is that process that wants to read from a file is instantly blocked, and some other program gets to run while the disk moves to the right location so that you can read or write. How many instructions could you execute during these seek times? Well, take the clock rate of a CPU and then figure out how many milliseconds that is for each clock cycle. That's roughly about how many instructions you can execute. Now, you can execute 1 instruction per clock cycle. That's not strictly true, but you can assume that. That's a good assumption. And then you'll see that you can execute on the order of millions of instructions during the seek time. Of course, now that we have SSDs, things are faster, but there is still a seek time that's about 0.16 milliseconds. So these are 10,000 RPM is a fast disk, and SSDs are even faster, but it's not instantaneous. So you still, even if you have SSDs, you still have the same problem. You have some finite seek time. You might as well let something else execute during that seek time. Network I/O can similarly be pretty slow. It can it depends on the server that you're trying to access. So you can have a latency of zero point 0.1 to 10 milliseconds. This is about the same range as disk access. So if you're trying to access something on the network, same thing happens. That's an IO, network IO, and then you get blocked. And when the data is ready, you get unblocked and you put into ready, so that whatever process that's executing, when that's done, you get a chance to run again. Okay. So here's the part of the operating system or the kernel that decides which process gets to run next. And that is the job of the operating system scheduler. We'll just call it scheduler. So we'll assume from now on we'll have very simple scenarios that we have a set of processes, and they're almost always called jobs. This is for historical reasons, because way back that's what they were called, jobs. And so these days we tend to use the word process. So, and then furthermore, just to make things simple, we assume that all of these processes like show up ready to run at the same time. That's certainly not realistic, but we'll relax these assumptions later and try to come up with a more realistic system. It turns out that these are good places to start. Then we'll say that each process only uses CPU time and does no IO. That's also unrealistic, really, but let's keep things simple, and let's just say that each process will only be like doing some number crunching, no IO at all. And then this is probably the most severe assumption, is that we know how long each process will run for. So of course you guys know that's not true, but let's just say that we have these three assumptions, and then later on we'll relax all of these. So the first thing we'll do is we'll try to figure out how these different schedulers, different approaches for scheduling will do based on one thing that we'll measure, that is the turnaround time. That is, we say, when did the job complete, when did the process complete, and then you subtract from that when the time that it arrived. So if they all arrive at once, and this is, let's say, time 0, and then the turnaround time for the job is whenever that one job finished. So each job will have a separate completion time, and then later on we'll see that each job will have a different arrival time too. Okay, so that'll be in the next part.